Hello, today me and my team members will present our research project about design and analysis of a hybrid power system for Grey River in Newfoundland. It is presented by Muhammad Kandil, Muhammad Ali, and finally Muhammad Aqli. The project was supervised by Professor Tariq Iqbal.
In remote locations, diesel generators are the choice for power generation. Diesel generators can be different power output depending on the scale of the electrical demand. For example, they can be portable, modular, or fixed. Another element to consider is that these diesel generators have a high power to weight ratio, making them an excellent power source for different systems. Furthermore, great diesel generators have two functions, providing electric energy as well as grid stabilization. However, from the year 1970 to 2010, there had been an increase of the global power consumption by 70%. Furthermore, 40% of the global emissions are accounted only for power usage by buildings. On the other hand, the world has renewable energy which can reduce operational costs by reducing the demand for diesel generators in remote locations and lower greenhouse gas emissions by lowering fuel consumption. One of the most popular forms of renewable energy is wind. It's prevalent because it's easy installed, easy operated, has low operational cost, and has ease in maintenance. However, a fully wind-based electrical systems, electrical energy output and efficiency are unstable due to instability in wind speed and current constraints. Thus, a result it helps to conclude that a mix of different energy sources is necessary to provide a stable and sustainable energy system for off-grid applications. A typical example of a hybrid energy system consists of a diesel generator, a control unit, and another power source such as a wind, solar, or hydropower. Therefore, to design a fully functional and efficient hybrid system, the wind speed, intensity of the sunlight, and water source availability should all be considered. Other design components to consider in the design process of such a system include but are not limited to overall system layout, hybrid system component size, and fuel price stability. Asif and Ghalib thoroughly researched the technical practicability and use of different roofs for PV system installation. The study was mainly focused on identifying the challenges that might be faced when applying PV systems. Based on the gathered data, specific platforms have a very high potential for applying PV systems as they managed to increase the PV array percentage to 11%. Bahura researched and developed an improved existing PV system in India. Bahura utilized PV System V 6.7 modeling software which helped foresee how much electricity can the novel idea possibility generate. The research include costs, payback period, and input and output energy to evaluate and measure the newly developed system performance accuracy. So far, it was proved that the newly developed system is more effective than its predecessor with reduction of 26 to 28%.
So now we will speak about how the simulation was created. The study required two different models to proceed forward. The first model implemented Homer Pro software to study and analyze the sizing and the economics of the model, while the second model implemented MATLAB Simulink to analyze the dynamics of the system as well as validate the system sizing of Homer Software Pro. The location for this study is Grey River in Newfoundland in Canada. It is a remote location that mainly depends on diesel power for energy generation. Grey River is a local service district and a designated site for 60 residential houses. Most of the peak loads are in the winter due to the lower temperatures, while in summer the temperature increases, which would not require space heating as an essential for comfortable living. The system requires 1632 kilowatt-hours of energy daily, with a peak demand of 240 kilowatts. Furthermore, due to the location geographical constraints, conventional PV panels, wind turbine, and hydropower were not feasible. This is mainly due to the town's location, which is surrounded by high terrains as seen in this picture. Adding to that, the river is on flat surface, which would not provide any surface head for hydropower implementation, which can be seen in this picture, which is marked as blue, which corresponds to no elevation. Therefore, a proposed system consisting of a mix of renewable and diesel energy would be the most practical in terms of application. The renewable energy would consist of a floating PV solar panels. Floating solar panels are PV systems that float on water surface of river, lakes, irrigation canals, or drinking water reservoirs. Floating solar panels are made of floating structure, a mooring system or anchor that the floating structure would be attached to prevent it from moving about freely on the water, a solar module and cables, as seen in this picture. The techno-economic study uses Homer Pro software to optimize the system and present the best feasible option. A PV array, battery system, and inverter delivering the load are all included in system design. The system design will include 3 diesel generators, PV array, lead-acid battery pack, and finally a converter to feed the load. 3 diesel generators were included because the community already had 3 diesel generators with a total capacity of 555 kilowatts. The project life is expected to be 25 years. The price for one diesel of fuel is assumed to be $2.08. The capital cost of the diesel generator is assumed to be zero, as the community already had diesel generators to feed the load.
In this part, we will talk about how the dynamic simulation system was built. The main purpose behind the dynamic simulation is to study and analyze the power output and storage of PV panels under the maximum power point tracking control, in combination with power generation from diesel generators, in addition to the system response when it's connected to the peak load of Grey River community. The system model consists of two main parts. The first is a DC system, which includes the PV array, buck converter, and batteries, with maximum power point tracking control, which uses the incremental conductance method, as shown in the figure, to control the duty cycle of the buck converter's main MOSFET. The second part of the system is an AC system, which includes the diesel generator and a transformer, which has one primary winding and two secondary windings to get a two-phase output which can feed the load. The two systems are connected by one phase inverter, which has a DC voltage input, and the output is one phase AC voltage with 60 Hz frequency to meet the Canadian standards. This inverter is a PWM controlled inverter. Also, the voltage is a pure sinusoidal wave without any harmonics, as we used LC passive filter.
Now moving on to the results of the Homer Pro model, the PV array had a maximum power output of 350 kilowatts, which equates to 1077 solar panels, and used a 300 kilowatt converter, while 250 kilowatt diesel generator would be used to supply the rest of the load. After optimization on Homer Pro, it was suggested that 28 strings of 480 volt battery pack would be used as an energy storage to provide stable power output to the load. Each string would consist of 40 batteries. 63% of the power would be generated by the PV panels as indicated by the results of Homer Pro. Therefore, the renewable fraction of the system would equate to 58.2%. As seen down in the graph, the PV panels produce most of the power in the summertime and the lowest in the wintertime, while the generator will produce the rest of the power to meet the load capacity. The system has a 4.26% excess electricity, while the capacity shortage is 0.5%. Therefore, the system configuration would be more than enough to handle the load. As Homer suggested, a total number of 1077 PV panels with a surface area of 2068 meters square. Therefore, the proposed project site has a total surface area of 3270 meters square, which would cover the PV array and the floating system. The covered area wouldn't obstruct any shipping lane, and the shipping movement can be seen in the dotted lines in the map. Now moving on to the results of the economical analysis of the system, the hybrid system's net present value is $3,714,574, with a levelized cost per kilowatt hour of $0.4878. The Canadian solar PV array had an initial capital cost of $245,592. There was not replacement cost as expected life is 25 years, which corresponds with the project life. Moving on, the cost of the battery pack is $483,761 with a replacement cost of $513,151, and the average life of the batteries is 6 years. Another system was created using only diesel as the only power generation to compare the economics with a hybrid model. The net present value of the diesel-only system was $5,627,837 with a levelized cost per kilowatt of $0.7391. Finally, the fuel for the diesel-only system is expected to cost $5,561,151. Therefore, the hybrid system would be more efficient and economically viable when compared to the current system that the community uses as a power generation.
In this part, we will discuss the final results of the dynamic simulation, which is done by Simulink. Homer Pro PV sizing is 1077 panels, so our simulation will use an array of 51 strings, and each string contains 21 PV panels to have total output voltage of 504 volts in steady state and after the transient response. Also from Homer Pro, the array of batteries consists of 28 strings and each string contains 40 batteries. The buck converter input voltage is 504 volts. This is from the PV side. Then it will be reduced to 480 volts in the battery side. After that it will be charged. This figure shows the battery state of charge, battery's current, and the total output voltage of the battery strings. The inverter output, as shown in this figure, is a pure sinusoidal wave, and also with frequency 60 Hz to meet the Canadian standard. As shown in the first graph, the phase-to-phase voltage is a 340 volts peak, with approximately 240 volts RMS. And in the second graph, the phase-to-neutral voltage for each phase, which has approximately 120 volts RMS. All the waves has 60 Hz frequency and pure of harmonics, with a quick transient response while connecting the load part by part in the system startup. As shown in the first graph, the total power consumed by the peak load of the Grey River community is approximately 220 kilowatts, and the system is able to feed this load with high stability. The second graph is showing the phase current for the two phases. We can see the transient response in the startup due to connecting the load part by part. Then in the steady state, it's a pure sinusoidal wave, with peak current higher than 1000 ampere for each phase, and it's varying by changing the load during the system operation to deliver the required power.
Based on the Homer Pro software results, the most reliable and economical design of the hybrid system which would provide the required electrical power for the load of community of Grey River would be the combination of solar energy and diesel energy. The results of Homer Pro software shows that the average daily load of 1632 kilowatts would require a total of 1077 solar panels, which would provide a maximum of 381 kilowatts, while a 250 kilowatt diesel generator would supply the rest of the load. The hybrid system net present value was 33.9% lower while the levelized cost per kilowatt hour was 34% lower when compared to the diesel-only system. Furthermore, the dynamic state modeling was simulated on MATLAB Simulink environment results shows that together the PV panels with the batteries and the diesel generator would be sufficient enough to feed the load at its peak. Therefore, the results demonstrate satisfactory performance for both the Homer Pro software and the dynamic simulation model. And thank you.